Okay, so far in this lecture we have described the basic language modeling problem. We've introduced a very important class of language models, namely trigram language models. And finally, we've spoken about how to evaluate different language models using this measure which is called perplexity. So in the final part of the lecture, I'm going to talk about estimation techniques for trigram language models, namely linear interpolation and discounting methods. And we'll first focus on this method called linear interpolation. So just to recap, one of the primary challenges involved in estimation of trigram language models is the sparse data problem that I described earlier in the lecture. So let's just go over this argument again. So a very natural estimate for a trigram language model is what is called the maximum likelihood estimate. So the general form is as follows. If I'm estimating the parameter q for some word wi, conditioned on previous words wi minus 2 and wi minus 1, then we simply define this parameter estimate as the ratio of two terms. On the numerator, I have what is often called the trigram count, and this is simply the number of times I've seen the sequence of words wi minus 2, wi minus 1, wi in my training corpus. On the denominator, I have the bigram count, and that is simply the number of times I've seen the words wi minus 2, wi minus 1 in my training data. So let's take a specific parameter as an example. Say I want to estimate the parameter corresponding to the probability of laughs, given that the previous two words are the and dog. I just have the ratio of these two counts, the trigram count and the bigram count. Now, as I said earlier, in general in these models, we are going to have a very large number of parameters. So if our vocabulary size is capital N, then there are roughly n cubed parameters in our model. As one example, if n is 20,000, then we have 20,000 cubed. That's around 8 times 10 to the 12 parameters. So even with the very large training sets that we use nowadays to estimate the parameters of a language model, this is a very, very large number. Now, because of this, inevitably, many of the counts used in these estimates will be equal to 0, and that will lead to all kinds of problems. In many cases, these q parameters will be equal to 0. That happens if this count on the numerator, the trigram count, is equal to 0. Worse still, if the bigram count is equal to 0, this count on the denominator, this estimate is completely undefined. So this leads us to the estimation methods we're now going to consider. And as I said, we're first going to consider this method called linear interpolation. So first, let's give some definitions. Q sub ml is going to be our maximum likelihood estimate, and this is the trigram parameter estimate based on the ratio of counts that I showed you on the previous slide. But in addition to this trigram estimate, I can also describe what are called bigram and unigram estimates as follows. So the bigram estimate, again we use Q sub ml, looks at a word wi and just the previous word wi minus 1. So this is an estimate which conditions only on the previous one word as opposed to the previous two words in the context. And again, this is simply defined as a ratio of counts. On the numerator, I have now a bigram count, and on the denominator, I have a unigram count. If we go a step further to the unigram estimate, This is actually an estimate of the probability of a word that completely ignores the context. So now we're not even going to condition on the previous word in the context. And this is again defined as a ratio of counts. On the numerator, I have the unigram count. That's simply the number of times I've seen the word WY in the corpus. And on the denominator, this expression here is going to be the total number of words in the corpus. So the total number of words in our training data. So this is simply a ratio of the frequency of the word WI to the total number of words I've seen in my corpus. So if we look at these three different estimates corresponding to these three different levels, they have different strengths and weaknesses. And the trade-off here is often referred to as the bias-variance trade-off in statistics. The trigram estimate has the benefit that it conditions on a lot of context, namely the previous two words, and so it has relatively low bias. Given enough training samples, these counts will be relatively high, and this will converge to a reasonable estimate of the probability of WI given the context. In contrast, if we look at the unigram estimate, it completely ignores the context, and so it'll fail to capture contextual effects, and so it will converge to a less good estimator as the number of training samples increases. Conversely, however, the trigram maximum likelihood estimate has this problem that many of these counts will be equal to 0. So we need a very large number of training samples to get an accurate estimate of the trigram maximum likelihood estimate. Conversely, for the unigram estimate, these counts will converge relatively quickly to their expected values, and this estimate will quickly converge to the true unigram distribution underlying the data. The bigram estimate is somewhere between these two extremes, where it conditions on a reasonable amount of context, and it converges reasonably quickly to its true underlying value. So what we'd really like to do is to come up with an estimator which trades off these different strengths and weaknesses of these three estimators. And this is where linear interpolation comes into play.